To introduce my colleague Salvador Barraza, and today he is presenting his talk entitled Wide-Invariant Dipole and Uniaxially Strained Graphene Insulator Modes. Please go ahead.
Okay, thank you. I will tell you about a paper by a girl named Engelke. She was a student with Philip Kim at Harvard. And there is a paper that came out in 2023 where they were discussing the topology of mores. Okay? Actually, I came across that work in 2021 at a presentation that Phil gave in Grenoble. But the paper took 2 years to publish. And that kind of gave a motivation for me to study topology. And so I will kind of report on what things that I have learned. This paper published in two weeks ago, and it was led by Angiolo Waman, who is a postdoc in my group, and that's him right there. Okay, so this is the outline, and there is 4 topics. I will actually sit for most of the time on topic 1, and hopefully I get to finish this presentation. Okay, so I will use half of the presentation discussing order parameters, and to be more specific, I will be introducing you to chapter 9 in Setsna's book, where a discussion of order parameters and topology is given, and to me it's kind of the clearest one I have found ever. Okay, so so let's get there. So this is the outline of the chapter, and we're just going to go point by point. Okay. And at the end, we're going to be able to understand Engelke's work and then Angiolo's. All right. So, okay, so before we discuss topology, and this was actually emphasized by Eduardo on the 2 presentations he gave, we need to first describe an order parameter, okay? The broken symmetry, which basically encodes a phase of matter, okay? And then at the end, we can begin discussing topology, okay? So in this program, the first thing one does is identifying that broken symmetry. And here there are 2 examples. If you have for example, some sort of matter that is isotropic upon continuous rotations in 3-dimensional space, then it will be described by a sphere. But then you can have collections of atoms that are arranged periodically. In that case, the symmetry is broken, and there is discrete rotational symmetries that replace, this continuous symmetry. In the case of ice and water, one will think of water as a time average over long times of the molecules kind of wobbling about. And in that sense, that time average is going to have, again, a continuous symmetry that is not present in ice. Okay, again, ice will crystallize onto a lattice like this. Okay. So once you identify the symmetries of your physical problem, then you can begin defining an order parameter. And Setsna has 3, and I will describe the 3 of them. And that's why this thing may go for a long time. I'll try to go fast. So the first example is that of a magnet. Okay, so you have a fridge magnet. Okay. And that thing is going to have, a sequence of domains, okay? And in configuration space or on your fridge, there is going to be a distribution of orientations of that magnetization, okay? And basically, the important parameter is the orientation of that magnetization, which can be mapped onto a sphere. And then this is that order parameter space, okay, for a magnet. Okay, so this is notation that Eduardo introduced on the second day too. So in this case, that order parameter is the sphere. These coefficients that we have here indicate the space or the dimension of that sphere, right? So if we had S1, that will be a circumference, S2 is a sphere, S3 is a hypersphere, and so on and so forth, okay? So then that's the order parameter for a magnet. Again, Sedna is kind of an old book, and so in the day, there was discussion of liquid crystals, and so in that case, their order parameter, a liquid crystal, it's also known as a nematic thing. It doesn't have an intrinsic polarization. It only has, some sort of axis in which the motion is defined. And the parameter space happens to be a hemisphere, which, it's written down as RP2, okay? It's a projective plane, okay? All right. So this is the one that is important for the presentation, and this is the one that has been discussed over and over. This may be the one that gives rise to Chern numbers and so on. And so here you have a two-dimensional crystal. The locations in dashed circles are the ideal locations of the atoms in the crystal. And at finite temperature or driven by some other means, the green locations are the actual locations of the atoms. There is this strain field that is described by this parameter U. This is elasticity theory. Okay, and so yeah. So then the order parameter space for these two-dimensional crystals is going to map onto a single unit cell. Okay, and these conformations that you can see here, U1, U2, and U0, actually map down to the same point on the unit cell. Okay, you can see that this U2 goes to the unit cell to the left, but this system is periodic. The parameter space is periodic, so U2 actually maps down to a point somewhere here, and U1 is on the unit cell to above. It will map down back to the single unit cell, and again, these 3 points go to the same one on that parameter space. Okay. So, so then in this case of crystals in 2 dimensions, the periodicity, the folding back of these parameters onto a single unit cell gives rise to periodicity, okay? And that periodicity permits folding this use back to the single unit cell, right? And so the folding is expressed by this double arrow. So then that's folding along one direction. That's a circumference, S1, right? And then when you fold on this direction where you have a single line, then that gives you this second fold. And then the outer product of this, of traveling this circumference either this way or this way is what gives you that topological order parameter, which for 2D crystals happens to be a torus. And this will work for, for sound. It will work for electronic properties as well. Okay? All right. So then with that, we move on. And okay, so the important point is that, in the conference, we have been talking about Chern numbers on and on and on and on, okay? And so the point I want to make is that you have to first see what parameter space you are in, right, in order to define your topological invariant, okay? That's the first point. And so then having said that, we continue with Sedna's program, and we examine now the elementary excitations. This is the physics, okay? Now this is the physics of the quasi-particles on these spaces. So now we go and discuss the physics. And he goes for the simplest example, not a 2D lattice, but a 1D lattice, and he's going to talk about sound. And so this is basically the physics of the problem. This is the solutions, the frequencies of sound relating to a stiffness, okay? And this is the wave numbers, okay? So this is the dispersion in this problem. This is the time. This is the solution of sound in the system, and so on. So I will not say much about this. This is just a comment in the book, but he makes a connection between these low energy excitations, the physical systems, the quasi-particles in a given physical system, with Goldstone modes. But I'm not gonna go there, okay? The only thing to emphasize is that once you have your parameter space, then you have your excitations, and this is again the physics. So in the case of magnets, you could have spin waves, you can have sound. In the case of a liquid crystal, you have these so-called rotational waves, okay? And then at that point, you can start discussing defects and topology, okay? So, so Sedna says that in the case of magnets, the most prominent defect is what's known as a hedgehog, okay? And it kind of looks like the charge, like the electric charge, right, onto a sphere. Okay, this is a magnetic. It kind of looks like a magnetic monopole. Okay, for the liquid crystal, you're going to have this sort of dislocation lines, and I will use most of the time discussing what happens on the crystal, because the mores actually have dislocation lines and so on. So I'm going to focus on this. This is similar to what Pavel showed you last night. You basically have a crystal, and then a line of atoms or a group of atoms is missing, okay? And that gives rise to something weird and topological somewhere around here, okay? So let's go on. Okay, so yeah. So this is then let's see, right, okay. Okay, so this is how one describes defects and topology on a crystal. This thing here, as you can see, as you are in the left, you have one row of atoms that's missing, okay? That's a dislocation line, okay? You want to notice that you can have dislocations that are horizontal or dislocations that are vertical, okay? And we're going to come back to this in a moment. But the idea is that in regions away from this sort of special part of the crystal, if you take this loop, okay, you are going to enclose 8 atoms, okay? So basically, you enclose 9 atoms, but you have 8 atoms that are closest to this loop, okay? But when you have 1, 2, or 3 or more dislocation lines, what happens is that the count becomes smaller, okay? So in this case, instead of having 8 atoms around, we have 7, okay? In solid state, people will call this difference a Burger's vector. It sounds like a hamburger. So I'm sorry, so forget my English. But anyway, so it's that's how people understand this. And it's basically a mismatch by a single unit cell, okay, that happens around that defect, okay? That's kind of the usual way to describe these things. But you can do something different. You can, loop around, okay, that defect, and use periodicity of your parameter space, okay? In this case, this is a periodic loop, so it starts at D, goes around a number of atoms, and it comes back at D, okay? So the first thing you do is you set the periodicity on the opposite direction to this loop, okay, so to say. And when you set the periodicity in this direction, what you end up with is a loop that cannot be contracted, okay? And that's because it's basically it cannot pass that hole, okay? So then basically the dimensions of this space are equal to one lattice parameter, okay? That's the distance that you go around, either in this direction or in the orthogonal direction. One lattice space, okay? Because that's the periodicity, okay? So it happens that in this case, that Burgers vector, whose length is one lattice parameter as well, is encoded in this winding, which is equal to 1, okay? If you had two dislocation lines instead of one, then this thing will wind twice, okay? And that's how you get integers out of these topological defects, okay? Now you can then, for comparison, you could try and wind in a region away from the topological defect, okay? And what you find is that in this parameter space, that winding will go somewhere else, okay? And this loop can be contracted down to a point, okay? And it gives you a winding of 0. So that this region here is trivial, okay? All right. Okay, so then I think this is, oh yeah, so then the thing to say is that, again, just to kind of give additional examples to things that Eduardo wrote down, this thing here is the so-called first homotopy group of the torus, okay? The subindices here that Eduardo was also careful to distinguish upper indices and lower indices. This means that we're using circumferences to study this topological space, okay? And this is the circumference, okay? If this number here is 2, it means that we have a space that we're enclosing with a sphere. We're wrapping that space, okay? But in this case, we have a subindex 1. It means we're just going on a loop, okay? Yeah, and so then this class is equivalent to C outer product with C, and that's because you can wind a topological defect around this direction or around this direction, okay? So this is a particular example where the topology is not defined by a single number, but actually by 2 integers, okay? All right, so yeah. Okay, then, in the case of the magnet, that hedgehog defect, this is the topology, this is the homotopy class for that. So again, these 2 means that instead of going for a circumference, we're actually wrapping this thing. So it's a 2-dimensional thing that we're doing, and this is working on a sphere, okay, S2. And the numbers that we get are integers. Okay, so this is what you get when you work, Gauss-Bonnet. So this thing, gives you integers. You want to notice that this number 2 that you get on Gauss-Bonnet happens because basically you are thinking of this 2 pi as a loop in 1 dimension. But if you were to think of this as a wrapping, then you will, want this number to be 4 pi, and this will be 1. Okay, just kind of a side comment. Anyway, okay. So, just for completeness, in the case of these liquid crystals, this is the homotopy that you get, and this happens to be basically the integers modulo 2. Okay. Okay. So with that, we go into this beautiful paper, at least in my opinion. with a lot of authors, some of which are mathematicians. Anyway, so let's get to this. So, well, maybe we read the title first. This is the topological nature of dislocation networks in two-dimensional Moire materials. So, okay, so we have everything, a dislocation we discussed. We're going to say that there is a network of dislocations that is topological in two-dimensional mores. Okay? We discussed mores earlier this morning, and so everything should be fine. Okay? Right. So, but maybe the first thing I want to say, risking running out of time, which I think I will, is that Moire is not a last name. Okay? Moire is actually a French word that means to wet. It has an Arabic origin. So anyway, no uppercase. Okay, good. And okay, so yeah, since I'm gonna run out of time, let me just kind of keep on going. Okay, so before discussing mores, let's discuss a bilayer. So let's go for that. So here I have 9 unit cells of a hexagonal, or honeycomb actually, two-dimensional crystal, okay? And I'm going to put another layer of that material on top of it, okay? These cost a lot of energy, okay? This is the so-called AA configuration, okay? And so basically, there is a cost of relative sliding of one monolayer with respect to the other. The smallest cost happens in these 2 points, okay? And the largest energy happens when the atoms are on top of one another, okay? Okay, good. So this is another example. Again, so you go for a horizontal displacement by this much. It's actually 1/3 of this horizontal line, and that gets you to the AB configuration. And if you keep on going for another 1/3, then you are on the BA configuration. And those are the 2 minima for this material. Those are the kind of preferred relative registries between the two-dimensional materials. Okay? Now you have a Moire. And in the Moire, you have a distribution of registries. Okay? So similar to the idea that we had in the two-dimensional crystal for that parameter U, here we're going to have a distribution of the 2 lattices. And you can see that. You can see, for example, here it seems like this is an AA kind of registry that repeats at the edges, and then there is everything in between. Okay, so then Engelke and collaborators define their topological order parameter in analogy with U. Okay, it's basically U. The lattice here is not square, but it's this diamond. But again, so the idea is that you have the 2 lattices. The displacement will be 0 when they sit on top of one another. That will be an AA configuration. And then depending on where you are on the Moire, the registers kind of vary. Let me just emphasize that in this case, this red line actually goes outside of the single unit cell. You have to fold it back into the single unit cell. This is another line that gets onto the neighboring cell. You fold it always back on the single unit cell. Okay? Okay, good. So again, this is how you see that there is a distribution of registries. And then, so this slide, what it has is 2 pieces of information. The first thing is that if you just put the 2 layers as a theoretician, okay, then this is the distribution of registries that you get. Okay? Because of the energy landscape, what will happen is that the material will actually like to have either an AB or a BA configuration, and this gives rise to these triangular domains on the Moire. Okay? And then the Moire supercell is basically defined by these 2 triangles. Okay? So the fact that the atoms wants to either sit on AB or BA configurations kind of makes these lines sharper. Okay? And the point is that these are the AA configurations, and they are avoided because they are too costly. Okay, basically you have to melt the material in order for that configuration to take place, or be at the temperature of the sun, or something like that. Okay, so it's not possible. And as I told you, in this paper, there is a collaboration with mathematicians, okay? And mathematicians are going to go for something like this. Okay, so, right. So, okay, so the distribution that we had of relative displacements is basically set to only 3 directions, okay? Colored green, blue, and red in that figure. Okay? Okay, so the other thing that they do is they say that the AA configuration is not possible. So this topological space is not the torus that we had you know, for the 2D lattice. It's something else. One way to think about this is, you know, as if you had a stump, you know, or some weird object here that will not allow, you know, the regular winding that you had on the regular torus. So this is kind of another thing, okay? Anyway, so the point is that, you know, this paper actually gets, you know, very deep into, you know, what now becomes a, an algebraic, an algebraic topology, because basically there is only 3 options. Okay, and you can build a group out of these 3 displacements, and this is how you avoid, you know, the AA site is here in the middle, and you have to avoid it, okay? And this thing here, basically projected back onto configuration space, gives rise to vertices, or, sorry, vortices or anti-vortices like this, okay? So kind of weird stuff. They even write down a non-abelian vortex theory and stuff like that. Okay, so I will not. It's actually a beautiful paper, but yeah, but there is no time to go into every detail. Anyway, okay. So right. So then the question is, okay. So the mores have this inherent topology to them, right? If we build vector fields that sit on the more, can we also get topology there? That's kind of the question, and that's, you know, the thing we did. But this is a previous example, okay? And what you have here is a more made out of a binary material. It's a hexagonal boron nitride bilayer, okay? The material is binary. It gives rise to intrinsic electric dipoles that fluctuate within the more, and that fluctuation is what they call a Meron, anti-Meron structure that you can see in this figure. So this is the in-plane intrinsic electric dipole, and this is the out-of-plane component. So the vector basically winds about in this kind of peculiar way, and so this is, you know, the one of the expressions we saw yesterday without the boundary terms and things like that. Okay, so then the thing is that, again, there is a topology inherent to the more, and that kind of lends a topology to vector fields that you put on that more. Okay, and so then what we wanted to do is put another vector field, and that vector field is the so-called Berry dipole. And okay, so okay, how much time do I have? I guess I'm 10. Okay, I should be able to finish on time. Okay, good. So okay, right. Okay, so now on to Berry dipoles. So Berry dipoles are they are vector fields, in-plane vector fields that arise when the Dirac dispersion is modified like this. So epsilon here is the Valley degree of freedom. If there is a strain on the lattice, there is an inhomogeneity of the Fermi velocities on the x and y directions. We also need to gap this, and this term here gives an extra tilt of the dispersion. This is a model introduced by Inti Sodeman, who happens to be German Colombian, and Liang Fu, This paper came out 10 years ago. And there is another model. It's kind of similar. This one relies on warping, you know, the non-Lorentzian part of, you know, that was discussed by Babak moments ago. So these terms over here, you know, they give rise to trigonal warping, and they distort the Dirac dispersion. And so anyway, so there are different ways to go about creating these dipoles, okay? And so once you have those terms on your Hamiltonian, you calculate the very curvature by usual means, and it will turn out that there is a momentum on that very curvature, okay? And that momentum is the very dipole, okay? Okay. So this is relevant because in the absence of a magnetic field, you can actually have Hall effects driven by time-dependent electric fields, but this is a second-order effect, okay, as you can see here. And okay, so this is how the very dipole looks like in the original model. So the symmetries of their Hamiltonian are such that there is a symmetry, mirror symmetry with respect to the horizontal axis, and that actually turns out the y component of the very dipole only. Okay? Okay, so I should probably skip some of this. The point is that there is a methodology to calculate the second-order currents in terms of these tensors. And the tensors, you know, are proportional to the very dipole, which is basically an integral of all the states up to the up to the chemical potential, okay? And this is what we are going to calculate on the Moret. This is what Angiolo calculated on the Moret. So okay, so then with that, we just go for that. So okay, so the Moret that we have doesn't take place due to a rotation, okay? In this case, it arises because we have two materials with different lattice parameters, okay? So hexagonal boron nitride, if you do 54 hexagonal boron nitride lattice parameters, that will be nearly commensurate with 55 graphene lattice parameters with 0.03% of residual strain. Is kind of good. And so this sets a supercell with this many atoms, about 20,000 and 6,000 carbon atoms, okay? And so we're going to be calculating the very dipole in this distribution of registries. So we do this using DFT briefly for every configuration, for every realization of relative sliding. We can calculate the change in the local potential, okay? And that change in the local potential is going to be fed onto changes of hopping integrals and on-site terms. So the changes in the on-site terms are going to give rise to mass. Okay, and the changes in hoppings are going to change the symmetries in ways similar to Fu's or Ortiz's models. Okay, so first thing to say is that you know, there will be two configurations in this lattice. Oh, I didn't say this, but for some reasons we decided that we were going to have an AV-HBN bilayer below graphene. At the end, that didn't matter, but it was kind of, we had already spent many months, but that's the system, okay? What matters is basically the interaction between graphene and the closest layer, okay? But yeah, it was late. We had spent too much time in this configuration, and that's what we did at the end. But basically, the thing you want to see is that when you are on the AVA configuration, carbon is in top of boron. When you are on the ABC configuration, carbon is on top of nitrogen, and this gives rise to a change in mass. Okay? And that change in mass relates to a change in the sign of that Y component of the very dipole. Okay? But if you, okay, so the ABA configuration sits right here, the ABC configuration sits right there, and if you get away from this horizontal line, what you see is that now the very dipole has horizontal and vertical components, okay? And not only that, it only points along 6 well-defined directions. And it gives rise to a winding that either goes anti-clockwise like this or clockwise like that. And with that, I just want to say that there are papers coming out. This one is from 2023. Here you have this kind of topological currents that are induced by light on A more A. And then we have Luis's recent work that just published maybe last week or maybe even this week, where you have graphene and you have 2 lasers. And depending on how you orient the lasers, you also have circulating currents like this. So, okay, and these are the references. And I actually appear to have finished on time. Do I have time to go through the conclusions or not? Okay. So, okay. So, so we spent too much time, maybe more than half of time, going through Setna, chapter 9, but I thought it was kind of nice. We learned about topology a lot in there, homotopies and things like that. Then we discussed this work by Engelke, where they discussed the topological nature of Moret superlattices. And then we fed a vector field, which is the very dipole, and we saw that it winds on this Moret. And with that, I finished. Thank you. Thank you so much.
Okay, we have time for questions or comments.
My question is related with the point symmetry that you have in superlattices.
Okay.
Which it is, because you see, you start with one that is some symmetry and you change it.
Yes.
Then it's a distorted lattice.
Yes, that is true.
It's
That's actually a great point. Yes. So thank you for the question. So there are 2 things to say about this. So the nice thing about these topological spaces is that they are periodic. So once one has a local registry, one kind of goes to that topological space, which is periodic, and then one can calculate the whatever vector field you want on that periodic system. That's related to what Babak was mentioning earlier. It's basically a semi-classical way of doing things. This will work well in the limit that the Moret length goes to infinity, okay, where you will have well-defined regions with a certain registry. But I believe, given that this is topology, that these things should have certain degree of reality to them. These fields are non-self-consistent. There are many other things that are questionable if you wish, but that's the idea. Yeah.
Just a very simple question. You mentioned in your work that you consider a bilayer, but an heterostructure, I think.
It's actually 3 layers. It's
and graphene.
Yeah, so we started this work from a very different route. We wanted to know if the very dipole was dependent on the stacking of the substrate. And we wanted to know if, polarized substrate or unpolarized was going to make a difference. We didn't see any difference. But I was reading Engelke, and then at that point we said, okay, we actually have something to say.
Okay.
It was a triple layer.
But I haven't done the question. So the question is that if in this case you also got some interesting properties as the graphene bilayer, like this superconductivity or this kind of stuff?
No, the dispersion is basically Dirac, and the distortions are, basically I mean, they are tiny distortions. Yeah, the gaps are of the order of, I think, micro electron volts in some cases. It is the small distortions of the Dirac dispersion, yes.
Okay, please, thanks again to the speakers. Thank you, Salvador. One short announcement. At the end of this talk, please remain in your place seated because Alberto has some message to conclude this conference, this meeting.
Okay.
Okay. The next talk is from Sendic Estrada Jimenez from the University of Chiapas, and he is talking about topological quantum matter foundations and application. Please come. Sorry? Oh, that's sorry. It's the other one. Okay, you can say. Excuse me.
Okay. I work thanks to the organizing committee for the kindly invitation for this workshop. I want in this talk I want to tell you about two concepts that related. I want related. One is an old concept arise many years ago that is non-commutative of the space, and another concept is an effective particles that arise in two-dimensional systems by description by quantum field theory. The outline of the talk is first a motivation to non-commutative that is from the some systems in condensed matter. After briefly the Moyal product that is a tools for apply this non-commutativity of the space in the systems, a brief of the Fermi liquid, and after we try to build a non-commutative Fermi liquid theory from the quantum field theory, after briefly about anions, and to motivation, also I built a non-commutative fractional quantum Hall effect from field theory, and final comments. This is not a final work, it's a work in progress with a student, but I think that is a nice idea, maybe a little naive, but I hope that, like you. Well, first, we consider two-dimensional systems within electrons, a perpendicular field, magnetic field. We choose the gauge, the Landau gauge, perpendicular to the plane, and we construct a classical Lagrangian. When we quantize this theory, we can construct this Hamiltonian with this pi is kinetical momenta. That this is a canonical momenta. That this have the characteristic that the commutation relation from the momenta is not commutative. When we calculate the eigenvalues of the Hamiltonian, as we know, is this form. In the limit, the magnetic field very great. We project to lowest Landau level, and the Lagrangian can be right in this form. Then the first term, we can see that, well, for one particle, for more clarity, is this form. We have this commutation relation for the coordinates, and this parameter we can label with theta. That is not commutative, not commutative parameter for the space. Also, these kind of theories arise in string theory from new usual fields with a B field in the perpendicular direction. This theory has the same form of the Landau problem. Then we can think that the non-commutative is natural origin in the systems of the condensed matter. I think that the non-commutative can be used as effective theory for show the non-punctual nature of the matter. The particles are not punctual really, then this has an effect in the interactions. This model introduces a non-commutative between spatial coordinates for avoid unitarity and causality problems. We maintain the time commutative, only the spatial coordinates are not commutative. This satisfies this relation, the time is commutative. For the study of the field theory in this space, we usually think of the formation of the product in the space of the function. The non-commutative space can be regarded as the algebra of the usual RD with the formation of the product of functions into the Moyal star product defined by this form. This is the principal motivation. We have an additional phase term that relates the product of function. One property of this product is that the quadratic part of the action in a field theory of a total divergence is exactly the same as in the commutative case. Therefore, the propagator remains the usual one, while the non-commutative modifies the interaction. For Landau Fermi liquid, they assume there exists a one-to-one correspondence between the electrons in a non-interacting gas, an ideal gas of fermions, and some elementary excitation of the interacting system known as quasi-particles. These excitations are characterized by its energy, caret EP. We assume that the ground state of the weakly interactive system can be generated adiabatically from some eigenstate of the ideal system. The effective interaction will be reflected in the behavior of the quasi-particles as effective particles EF, that is, free particles derisked with the interaction. This is a picture. Then we have this relation, the particle, quasi-particle, the kinetic energy, this energy epsilon, the total energy as the sum, the density of the state. This is not the sum, only the density of state with kinetic energy. This theory is valid only near of the Fermi surface because the time of life of these quasi-particles is proportional to this relation. And near this Fermi surface, we can expand this energy in this form. We have energy, the Fermi energy and the Fermi velocity with the moment of the particles. In the case when this excitation corresponds to real particles of system, we have obviously the Fermi velocity is this form. The total energy of the system is not the simple sum of the individual energy of each quasi-particle. It is necessary to consider an expression to second order as follows. And this function f is a second functional derivative of the energy respect to density functional and is known as the interaction term of the quasi-particles. And this is the principal contribution of the Landau theory for Fermi liquid. For Wild quantum field theory, we construct an effective action. We adopt the Euclidean formulation of the functional integral formalism for a system of interacting fermions. Its partition function is given by this expression. These eta are auxiliary source, and the phi are the fermionic fields, which take as Grassmann variables. Is 0 is the free action, and I is the interaction term. For usual Fermi gas, the 2-point function is given by this green function, and the principal modification for Fermi liquid is a change for the kinetic for this energy. Since we are interested only in the correlation at low energy, let us define two sets of variables for for low energy, for high slow mode and fast mode are called. So action can be divided into two parts, corresponding fast mode and slow mode, and total action can be written in this form, and we can calculate the partition function by means of cumulant expansion, that is the formula. Then we construct an effective action which defines a new coupling function with the fields. This new function must be compared with the original ones in the action, but these quantities are defined in different kinematic regions, this and this respectively. So it's necessary to rescale the momenta in this effective action to recover the original scale. We also rescale the fields to define the new fields. It is a renormalization procedure where we choose the real prefactor, so that the quadratic part of the action terms the new fields have fixed coefficient, and we have a fixed point for this theory. In particular, for our theory, the free action is given by this expression. In this expression, sigma is the spin index, and E epsilon f is the Fermi energy that corresponds to chemical potential at 0 temperature. This is a summary of the process. As we are interested only in the region nearest of the Fermi surface, the kinetic energy can be expanded, as I told you before. With this composition, we can rescale the momentum, this form, in the fields rescale as this factor. We will focus on studying the Fermi liquid in a two-dimensional plane with a circular Fermi surface. It's a toy model. In polar coordinates, the free action becomes in this expression, and the non-commutative do not play a role in this level. For interaction term, the non-commutative plays a crucial role. We have a quartic interaction term in the coordinate representation. We can write this form. We consider only non-commutativity with the spatial coordinate, and our potential is time independent. So we can write the integral as this, with this delta. To make consideration of symmetry and construct simpler, we will work in momentum space. The above expression can be rewritten in this form. We have this is phase characteristic where we write explicitly the star product of this form. For usual commutative cases, it is necessary to impose that the interaction potential be antisymmetric with respect to their variables in such a way that the action is invariant on the change of the order of the fields that give this result. However, for our present case, we have an additional phase factor coming from space non-commutativity. The presence of this factor makes the symmetric consideration in the non-commutative case a bit more complicated. That implies the action we can write the U potential that is the B with two phase terms. As a particular example, we can simplify the B local potential by taking it to be a local integration or coupling constant, but assuming that is only delta. If we make the same procedure, the interaction action can be reduced to this form. This is, for this, we are not considering fields with spin. There are fields without spin. And we have this minus sign that implies that for theta equal to 0, this term is 0. That is that we hope, because in classical for commutative case is fields without spin. There are no internal degree of difference. There are not 4 interaction terms for Fermi liquid without spin. Then we can see that no commutative include this additional term for Fermi liquid for fields without spin. We recall briefly the anyons. We have a Fermi we permute two fields twice. For Fermi statistics, this phase term is equal to 1, to both is equal to 0. These particles only exist in 3D. In 2-dimensional, not necessarily have only these two statistics. There are fractional statistics. This alpha can take any value. These the particles are called anyons. Double permutation is different to identity than to we have some constriction in the phase for the wave function. This is the relation that in 3-dimensional the phase transformation corresponded to Sn group, in 2D corresponded to braid group, as tell you Professor Eduardo. We are also for my idea, we talk briefly about the non-commutative quantum Hall effect. We are considering a fermion field coupled to a Chern-Simons gauge field theory, an external electromagnetic field, also considering an interaction between fermions. The total action describing the system is this, the Chern-Simons materia interaction, with each part is given by this way. This total action is invariant on the following gauge transformation, and this with the modal product let us define a covariant derivative in this way. D mu in D mu dagger. We use the constriction for the Chern-Simons field, and the non-commutative field is in momentum state, is working in momentum space. This action can be written in this form that is very large. We use the Fourier transformation for density in this, defined for Moyal product in this way, and replace this product with this constriction. Let's reorder the action, then each term is in this way. We have an additional term in this description given by this form. The point here is that as for Fermi liquid field theory, the propagator is not changed, but the modification or the dual non-commutativity come from the interaction vertices. In this case, is have this form for gauge fields with the matter. Then we can see that these phase terms for some fixed momentum have a parameter free theta that we can modulate for maybe represent to anion in some theorem that is our home. The phase additional terms that are due and non-commutative of the space can be related with the phase factor of the anion field, and maybe can fix the theta parameter of the Moyal product according to the kind of anion in the theory. This is the theory or the model that is constructed with my student. Here, playing with some models to try to relate these phase terms. Well, this is what I like to explain to you. Thank you.
Questions or comments? Oh, yeah.
Thank you. There's something I think I didn't understand quite well. Maybe 2 slides before this one, when you wrote the gauge transformations of a field. Another one. Why does the Moyal products enter there in the? Because I mean, lambda here is a gauge parameter or what?
Yes, it's a gauge parameter.
Right. And how is the Moyal product defined between the fields and these parameters?
Let me remember. It's an auxiliarity field for describe. For construct these transformations of gauge, we initially take the usual definition of the commutator of the structure constant of the gauge fields, and to make invariant the theory, we see that only with this part for phi and minus this part for psi dagger, we have a theory invariant. The gauge field, we have the usual form, this term with an auxiliary field.
So lambda is an auxiliary field.
It's auxiliary.
Okay. So yeah, that's what I was not understanding.
Yeah.
Thank you.
More questions? Okay. So we thank again to Cindy.
Thank you.
Muy bien. Aquí no hay foto.
Sí, no, no, ya.
Okay. Just one short announcement for all the people attending this meeting. You can pick up your certificate just outside in the table. And the next is Alberto.
So it's brief. So here's the time to conclude this event and say goodbye to all of you. On behalf of myself and the organizing committee, Professor Luis Urrutia and Professor Eduardo Barrios, I would like to thank you for being part of this event. The second edition of the Topological Quantum Matter Foundations and Applications has been especially organized to bring together national and international experts working on the different aspects of topological quantum matter to emphasize particularly the interbreeding between condensed matter and high-energy physics. Also, the event has the double purpose of fostering related research in Mexico, as well as promoting further collaborations. So I very much hope that this was the case. To close this event, I would like to express my gratitude to the CONACYT, the Instituto de Ciencias Nucleares, and Facultad de Química for their invaluable support in completing this event. I would like to thank all the speakers, nationals and internationals, and participants who have visited us and have attended the entire program with so much of patience and interest. Finally, I can say again, thanks to all of you, and we see you in the next edition of the Topological Quantum Matter. So, thank you.